We wanted to build a drone that could fly around an indoor space without a human piloting it. We felt that it would be useful for exploring areas that people couldn't get to, or to get information about unknown areas that would be dangerous for people to enter. Rather than buying an already built drone, we decided to custom build ours. This allowed us greater flexibility in our choice of parts and how to put them together. We had to get our drone up and flying, and for this we used a Pixhawk flight controller with ArduPilot software. Once we built the drone and installed the flight controller, we had to do some calibrations before it was ready to fly. Then we started off flying the drone with only the flight controller on board to make sure it was stable. Then we added the computer and finally the Kinect sensor to make sure it could lift all of the weight. Once we had achieved manned flight, it was time to work on autonomous flight. We used an NVIDIA Jetson TK1 as our computer, and we attached an Xbox 360 Kinect to it. Getting the Kinect sensor up and running was a challenge, because it uses proprietary Microsoft drivers. To get around this, we integrated ROS, Robot Operating System, into the project, which came with several packages that were useful later on. Once we got ROS up and running, we were able to see the Kinect sensor data as a series of 3D point clouds. Once we had the Kinect sensor working, we installed a SLAM package to get a position estimate. SLAM stands for Simultaneous Localization and Mapping, and it allows the robot to estimate its position and its environment while it is getting new information about the environment, much the same way a person does when she walks into a new room. We used the RTab map package that comes bundled with ROS because of its speed and its ability to correct itself if it loses some frames. Once we had the SLAM algorithm working, we could use the position estimate to navigate the room. Navigation was the biggest challenge in this project because the ArduPilot software we used didn't support autonomous navigation indoors. To get around this, we had to spoof GPS coordinates so that the flight controller thought there was an attached GPS module. Once we did this, the software allowed us to send it waypoints that it would try to follow. We were able to send the drone waypoints to follow, but because of the time constraints, we were unable to get the drone's movement to be precise enough for use in a demonstration. So we demonstrate instead that our drone can map a room while being piloted remotely. We plan to continue the project beyond this class and have some planned features. We plan to use an optical flow sensor to give the robot a better position estimate. Initially, we assumed that the position estimate from the Kinect would be sufficient, but what we learned was that in practice it was too difficult to have the drone fly precisely enough for the position estimate to be useful. Instead, we plan to attach a downward-facing camera known as an optical flow sensor to allow the drone to get a second 3D position estimate that can be used in conjunction with the SLAM position estimate to make it more reliable. We also plan to continue working on autonomous indoor navigation using other ROS packages that plan out an exploration strategy for an unknown room. We had a lot of fun building this drone and learned a lot about sensors and embedded systems. The biggest lessons we learned are number one, that tasks that are seemingly easy will not necessarily take a short amount of time, and number two, that while software may be easy to debug because you can execute code quickly and get instant results, debugging embedded systems is much more time consuming because there are so many pieces that can break, and fixing them can take time because you have to physically take things apart and put them back together.